difficile.
No, it's not difficult. We're trying to help you and we provide the subject, but
Okay.
it was not our job.
Sure. No.
Pigliano ciabatte italiana, ci sono italiana, quello sopra. Ci sarà un uso libero e lasciamo la ciabatta qua. Dovete salvare.
Mark? If you need it, thank you. Appreciate it. All right. Good morning, people. Hi. As usual, in this part of the world, things generally start a little slower than normal, and that's okay. Our first speaker has not arrived yet, Dr. Binder. I'm sure he'll be here soon. So we're going to go ahead with the introductory session, hopefully. So can you load up the first talk, the introduction talk, please? AV guys? Yes, great, okay. Well, good morning, everybody. I'm Susan Bookheimer. I'm going to be chairing the session today. We're starting with many new systems, so we are cautiously optimistic that this will work. Has everybody downloaded the OHBM application already? If you have not, go ahead and do so. We have internet here. You'll be looking at something like this. So if you get on your first day on that red menu and click on events, then it will bring you to this session, and you have to browse by day, and then go to Sunday, and then move on down till you get to our session, and then click on the session. And then at that point, we'll be asking you some questions periodically. We didn't put too many in because nobody's really confident in the system. And also, you can ask questions without raising your hand. You can also raise your hand. We encourage raising your hand. And there are also microphones over there. However, if you want, you can just type a question. If you just scroll down to the bottom there, it'll says social Q&A, and you can ask a question and just type in whatever you'd like. We'll be able to see your questions up here, presumably, and if all goes well. And then we will be able to answer them sort of in real time. So we're going to try this out. Let's see how it goes. Okay, did you guys get a question on your apps that says, what is your area of specialization? Did anybody see that? Nope. Okay, that does not bode well. Okay. I didn't either, so, okay. So I was asking what your areas of specialization are. How many of you here are neuropsychologists? How many are neurologists? Radiologists? A couple of radiologists. Neuroscientists? None of the above. Hi, Natalie. None of the above? None of the above. What are you? I'm sorry, I should have said that. Statisticians. Actually, that was one of the answers, I think. Okay. So we're going to talk a little bit about, in general, about functional MRI, and then I will go into the memory session, and then hopefully between now and then, Dr. Binder will have arrived to do language, and if not, we're going to go ahead with the statistics. So I asked the general question, why is clinical fMRI different from all other fMRI? And there are many answers to that, but overall, the big picture answer is many of the rules of good research practice that you have learned for years and years don't apply in clinical fMRI. We're increasingly under pressure as neuroscientists to use larger and larger and larger n's, whereas in clinical fMRI, you're using an n of 1, really small n. So everything you're doing is a within subject experiment, and you need to have enough power to do that. We also will change the experimental design and experimental parameters for each of our subjects, and that's completely different from what we do in our typical fMRI, where we are doing exactly the same thing for every single person, and we're being very, very careful to do that. As others will show when we do some live analysis, sometimes we have to make up what we're doing on the spot, and we do a lot of variations depending not just on the person's level of function, but also on what where their lesion is and what the goals of surgery and what the individual subject's goal of surgery is. So we'll show you, I think, some strange cases later on. We're usually told that we use these strict statistical thresholds, and they tend to be constant across everybody. And as Dr. Purnett will talk to you about later, we cannot use that approach. We have to change thresholds for every subject. And I think one of the most important differences, which you'll hear about later on today, is that unlike most of science, where we want to avoid false positives, that is, we never want to say anything that turns out not to be true, in clinical fMRI, we want the opposite. We want to avoid false negatives, and we want to do that a lot more than false positives. Of course, we do want to avoid false positives as well, but it's way more dangerous to say that an area does not have activation, go ahead and cut it out, than it is to say the area does have activation, you may want to be careful at that area. And unlike your normal neuroscience, if you are wrong, the consequences are extremely high. A patient could get severely damaged, for example, if you're wrong, whereas typically somebody fails to replicate your work and they write an article about how poor your paper was. It's humiliating, but not deathly. And of course, the other thing is that you actually need a license to practice a clinical fMRI or an arrangement with a licensed professional. And there are some groups that will do that. They'll work as teams together because In fact, most neuroradiologists are not trained either in neuropsychology or in statistics. And so I think overall we'll be advocating a team approach to this. Accepted clinical uses of fMRI, and I can't speak to other countries, but we do have speakers from other countries who can tell you about what their laws are. But in the US, pre-surgical planning is the only FDA-approved use of clinical fMRI. Interestingly, there is no mention of what kind of surgery. It just says pre-surgical planning. The assumption, of course, has always been that it's mapping for epilepsy or for focal lesions near language and motor and memory areas, but there's no reason that it can't be something else. And in fact, increasingly, we're getting requests to do fMRI for psychiatric applications. So for patients who are getting deep brain stimulation or other kinds of psychosurgery, targeting for TMS or targeting for DBS. We don't know how to do that, and we're actually not going to be talking about that today, although we'd be happy to answer questions when the discussion comes up about those topics. And I think going further, we'll see a lot more of that. We'll see targeting for neurological disorders as well as psychiatric disorders in the future. The other thing that's peculiar, even though that this is an FDA-approved procedure, there are no standards of practice for this procedure. There are no standards for applications, but there are also no standards for what tasks you can use or cannot use. There are no standards for applications for analysis methods as well. One thing that is also different in the US is that clinical fMRI is the only radiological procedure which can be billed for by not just a neuroradiologist, but also a neurologist or a neuropsychologist. So as a neuropsychologist, which I am, I can bill the professional fee for functional MRI. And there are no other applications like that in the United States, and I'm not sure what the laws are in EU, but hopefully you'll hear about that very soon. So why did we decide to do this workshop? So there was a white paper that was put out by the ASNR recently, and I have enclosed the reference here for you, and strongly suggest that you pull it down. And the article reviews what are the most common practices in clinical fMRI and essentially advocates for those. And we put together a working group on clinical fMRI with OHBM. So the speakers, or most of the speakers from today's session, are part of the OHBM working group on clinical fMRI. So we, and I use the royal we, have written, it's actually mostly Natalie Votes, who's speaking later today, has written, and we as a group will soon submit an alternative white paper that reflects the views of OHBM. So as we're putting this together, if you have comments that you would like to add, we will incorporate them because we haven't submitted the paper yet. So the group that is presenting today represents a very wide range of expertise who are doing different applications and use different analytic approaches. I have found that for those of us who do clinical fMRI, we all do it our own way, and we feel very, very strongly about how we do it. But we have with us today, graciously, Mark Jenkinson agreed to come, and he will speak about rigorous statistical design, and Cyril Purnett will speak about other issues that are critical in statistical analysis, and to some extent will reflect some different points of view. So today, what we're hoping is that together we're going to present what I hope is a comprehensive guide to clinical fMRI approaches, talking about all of the different problems that come up, and also integrating this with the surgical teams, and we'll be doing some real-time case analysis. So Dr. Walshaw, who's my colleague at UCLA, will be presenting on real-time analysis for surgical cases, tumor cases, who we generally have to turn around sometimes within a day or two. So here are our speakers today. Jeff Binder is our first speaker theoretically, but in reality he hasn't arrived yet, so we will just keep pushing him off until he actually comes. So I will go after him. So Dr. Binder is a neurologist who's been working in epilepsy for many, many years. I'm a neuropsychologist. Mark Jenkinson, who is from Oxford and now from Adelaide, as you all know, is an expert in statistical analysis. Cyril Purnett, who's not at King's, he's actually at the University of Edinburgh, is a cognitive scientist, but he's going to be speaking about statistical issues. Dr. Walshaw is a clinical neuropsychologist, and she's actually a pediatric neuropsychologist. Michael Zani, who is my former graduate student, is a radiologist and a neuroscientist. He got his PhD in neuroscience at UCLA and is now professor at Stanford. Andreas Bartsch should be here. He's at University of Heidelberg, and he is neuroradiologist. Natalie Votes from University College London is a neuropsychologist, and she'll be doing a really nice presentation on integrating with intraoperative electrocortical stimulation mapping. Linda Dowes from Amsterdam, she'll be talking about resting state, and Andreas will hopefully come back and talk to us about a new technique, cerebrovascular reactivity mapping. We'll have time for questions and discussion and controversial issues after each section. So these are 4 sort of discussion topics generally. So after every couple of talks, we'll have a discussion and a break. We have general discussion topics here, but we can stray outside that depending on what you would all like, and a general Q&A. So not knowing if any of our devices are going to work, I've asked if there are any burning questions now, and maybe somebody can go to their app and see if we can figure out how this works to ask a question. Can somebody ask me a question? And I'll see if I can see it. Anybody got a question? Mark, can you tell if we are... You asked a question? Okay, let me see if I can find it. The AV, as you can see here, is still a work in progress, as we shall say. Okay, let me see if I can see it. I can't see it, so go ahead. You're just asking one, okay. Okay, I do not see any questions. You can see them on the app? I can't see them on the app. Okay, I'll ask, can you see it on the app? Okay, all right. Well, I'll get somebody smarter than me to ask questions later, and we'll have somebody who can actually read them. I should be able to do this on this app, but right now it's not working, and I don't want to do this in real time. Okay. Okay. That'd be great. Thank you. Okay. Okay, so there's a question back there? Oh, there's Jeff. Oh my gosh. All right. Okay. Great. Okay, I'm so glad that Jeff is here. So the first talk will go on as normal, the language talk by Dr. Binder. And so I would like to introduce Dr. Binder, who is going to be talking about language. And Dr. Binder is from the Medical College of Wisconsin. He's a neurologist. He's the token neurologist, I believe, for today. And I've known Dr. Binder for many, many years. He is an expert in epilepsy and in language mapping, and I think most of us will be citing his work in our talks. And are you all set? Okay, all right, welcome, Dr. Binder. Good luck with this. We have no idea if anything works. Nice to see you.
I prepared some of the response questions, and I had 2 of them. I just had no confidence that the system would work, so you're not going to get them. Well, I could ask the questions the old-fashioned way and with a show of hands. How about that? How many people in the audience would agree with the statement that the awake resting state is associated with very little neural activity? Okay, good. I'm going to talk about language task selection. That's the main meat of the talk. It's a big topic, as you all know. It's usually a thing I spend an hour on. I'll try to say as much as I can in about 20 minutes. And then I wanted to talk about predicting naming decline with fMRI after left ATL, anterior temporal lobe surgery, which I think is one of the main clinical indications for pre-surgical language mapping. And also touch on predicting verbal memory decline in the same population. Okay, well, we don't really think of the language system anymore as Wernicke's area and Broca's area connected by a wire called the arcuate fasciculus. It's a little more complex than that. This is a diagram that I think is useful for people doing clinical language mapping. There's a region in the anterior superior temporal sulcus indicated in yellow in this slide that processes speech sounds and recognizes consonant and vowel sounds. We call that phoneme perception. It's organized bilaterally, so unilateral damage usually doesn't produce any clinical deficit. When there's bilateral damage, you get a syndrome called pure word deafness, but that's rare and not going to happen in a unilateral surgery. So that region of the brain you don't have to really worry about much if you're operating on patients. The big blue area, which some people refer to as Wernicke's area, has nothing to do with language comprehension. So that's number one strange new finding over the last 20 or 30 years, that the area that we think of as central to language comprehension in the posterior superior temporal gyrus, supramarginal gyrus, doesn't have any role in speech comprehension at all. What it does is it represents speech sounds internally, and so it's useful for producing speech. When it's damaged, you get phonemic paraphasias, but no comprehension disturbance. That's a syndrome called conduction aphasia. And it's also useful for keeping phonological information like telephone numbers and digits and things like that online in a working memory buffer. But it has nothing to do with speech comprehension. Speech comprehension does depend, and language comprehension does depend on this large zone in red here called the semantic store, which covers most of the lower 2/3 of the temporal lobe and a lot of the inferior parietal lobule. And then in the frontal lobe, you have these control systems that either the green area in the inferior frontal gyrus connects mostly with that phonological system called Wernicke's area, whereas these other regions in orange connect mostly with the semantic system. All right, so first really important point I want to make is that there is no such thing as language fMRI if that's used in an unqualified way. There are different language paradigms that produce very, very different activation patterns. And so if someone stands up here and says, I performed language fMRI on somebody, you need to know what the protocol was and how the control and activation tasks differed in terms of cognitive processing. Sorry, I ran up here, I'm a little out of breath. So these are activation patterns induced by this word generation task that's commonly used in clinical practice. These are two results from two different labs, two different groups of patients. These are group maps. And you can see that there's a lot of consistency here when you contrast that task of generating words in your head with a resting state. You get this map, which is left lateralized inferior frontal gyrus activation primarily. There's really no or very, very little activation of temporal lobe language systems that I showed you on the last slide. Yeah, but here's a different language fMRI task that we developed and was adopted by the Human Connectome Project, contrasting a story comprehension task with a mental arithmetic task. And you see that the activation in the temporal lobe is very strong, robust, diffuse. So these are both language fMRI protocols. They almost have no overlap with each other. Which one is right? Which one is important for clinical mapping? I would say probably both. Here's another example that's kind of dramatic, I think. This is a contrast that we use in my lab and clinically, and I'll talk about it more in a minute. We've published a lot on it, compared it to the WADA test, used it to predict verbal outcomes after surgery. And as you can see, there's a strongly left lateralized activation pattern here. This is a task comparing hearing words, making a semantic decision about them, and the control task is hearing tone sequences and making decisions about these nonverbal tone sequences. This is the pattern using the same semantic decision task, but with a different control of resting. And you can see that the pattern here has almost no overlap with the one on the top. It's a different control task. It's not very strongly lateralized, a little bit in the frontal lobe. And a lot of these regions that are activated, shown in the blue circles here, are missing when we use the resting control state. So here is a dramatic example, I think, of how language fMRI mapping can be insensitive to detecting certain brain regions if the wrong task contrast is used. We also get these auditory systems, primary auditory systems, and attentional networks in the anterior insula and elsewhere bilaterally when we don't control for those non-linguistic processes. So here's what we do, I think, and here's what I advocate when you're setting up a language mapping paradigm, is to analyze the processes that go on in the task. And I'm going to use that semantic decision task as an example. So say the task was, you're going to hear names of different kinds of animals, and what you do is you press a button when you hear a word that is a certain kind of animal. Say it's found in the country that you live in, or it's larger than a cat, or it's useful to people. So here are some of the brain processes that are engaged during a task like that. There's, first of all, a motivational system, which is in the medial part of the frontal lobe for the most part, but also in basal ganglion, thalamic areas. The person you're scanning is either going to care about doing the task and making you happy, or they're not. And if they do, they're going to engage that motivation system. There's no way around it. It would be true of any task. They also have to direct attention and effort at the task. They have to keep the task instructions in working memory, regardless of what the task is. There's a working memory component to the task that's not necessarily linguistic in nature. Because we're using auditory signals here, there will be pre-linguistic auditory processing of the signals that are coming into the ear. And that would be true if the signals were words or tones or whatever. In this case, there's also this process I referred to before as phoneme perception, mapping the acoustic signals onto consonants and vowels. There's then semantic retrieval. So we're asking the person to make a semantic decision to identify the meaning of the word that they hear and make a decision about it by retrieving information. So if I say frog, and the task is to decide whether the animal is larger than a cat or not, you will have to retrieve a mental image of what a frog is and its size. Phonological short-term memory is necessary, this process I talked about, because while you're making that semantic decision, while you're mapping the information to semantics and retrieving the meaning of the word, the signals, the consonants and vowel signals, have to be retained, even if only for a half a second in this phonological short-term memory buffer. There's semantic short-term memory, because as you're making the decision about the frog, you need to keep all of that information that you've retrieved in a semantic short-term memory buffer. Then you make a decision about which motor response to make, and then you execute the motor response. So all of these processes will be activated by this task that seems like it's a language task, and it is a language task, but there also are all these other networks in the brain that are activated by this task that are not language areas. And so there's the specificity problem with fMRI language mapping. You may activate brain regions during a language task, but if you haven't built in the proper controls, these activated areas may not be linguistic in nature. So what we do is design control tasks like the semantic decision task I've described here. In this case, the subject presses a button, they hear sequences of tones and their high and low pitches, and if they hear a sequence that has two high pitches in it, they're supposed to respond. And we analyze that task in the same way that we did the semantic decision task, and what we discover is that that tone decision task will activate the motivation, attention, working memory, auditory processing, decision, and motor response systems in more or less the same way as the semantic decision task. Not exactly the same, but good enough for clinical mapping, let's say. So we're left with, when we do a task subtraction, these systems that are more or less specific to language processes at different levels. And so, here's an example. Again, the same maps I showed before, just zeroing in on a couple of slices and highlighting the early auditory areas in the superior temporal gyrus. So many people would see a map like this and say, aha, Wernicke's area, but actually that region is activated just as much by the tone decision task as it is by the word decision task. And it's activated bilaterally. It has nothing to do with the language per se. It's involved in low-level auditory perception. And these attention systems in the thalamus, basal ganglia, and insula that I mentioned before. Keep in mind, these are slices through the right hemisphere during this supposed language task. But when we contrast that same task with the tone decision control that I described before, all of these regions are subtracted away to our benefit. We've identified them as not specifically involved in language processing. Okay, and the next topic, so that was a few slides about controlling for non-linguistic domain general processes that you don't necessarily want to point to in a patient and say, that's a critical language zone if it's not a critical language zone. So that's the specificity problem. Now we can look at one aspect of the sensitivity problem, which is this problem I refer to as the invisible semantic network. There are many, many language paradigms out there that do not activate this big red zone that I've identified as the semantic store, and we need to have an understanding of why that is. So here's two examples, the verbal fluency versus rest that I showed before, this map in the middle. There's no activation of this semantic store system. And the other one would be our semantic decision task. Even though it's a semantic decision task and presumably activates this semantic store quite a bit, it doesn't show up on the contrast with the resting state. And yet we know that it's possible to activate this region. This is a meta-analysis map that we published about 10 years ago on 120 different semantic imaging studies. So these are carefully designed studies to isolate semantic cognition, either highlight the semantic stores or the semantic control areas in the frontal lobe. And when you do an average of all those coordinates that are published out there, you get a map that looks very much like the cartoon that I presented up in the left upper corner. So it is possible to activate this semantic system. And here's another example. So in this case, we've contrasted the semantic decision task with the tone decision task. Same map I showed you before, and you can see activation of the angular gyrus here, the semantic store in the inferior parietal lobule, and activation of the ventral temporal lobe, another area of semantic storage, and activation of a large semantic control network mostly in the pars orbitalis of the inferior frontal gyrus. And here's that map that I showed you before. Instead of the control task being tone decision, the baseline is the resting state. So what's wrong here? What's going on? You probably mostly know the answer, but I'm going to say it anyway. The problem is with the resting state, which is not a resting state. There is a lot of brain activity that goes on during rest. We can rest right now. Let's do it for 10 seconds. Rest. Clear your mind. Don't think about anything. I'm going to claim, maybe not everybody in the room is self-aware enough to confirm this, but I'm going to claim that there was lots of mental activity going on just then. Maybe you were counting down the 10 seconds. Maybe you were wondering, why the hell is he doing this to us? But I would claim that there's lots of mental activity going on. Maybe you were thinking of where you're going to meet that person for lunch, or what you'd like to have for lunch. So this is a figure from Randy Buckner's Brain Default Network Review, and he points out that during passive states, when you're not really required to do anything, your mind tends to drift, and we call this mind wandering or task-unrelated thinking, some people have called it, or mentalizing. And it turns out that this topic of what people think about, what's the content of their stream of consciousness, has been exhaustively studied in the last 10 years. And before that, it was mentioned by William James in the 19th century, and it was studied in the 60s by John Antrobus and Jerry Singer and their colleagues. And nowadays, it's a very hot topic of research. And so people like Jessica Andrews-Hanna here and her group have polled or asked people after a resting period what was in their mind, what was going through their mind. And often it's things about planning the future, remembering the past, thinking about things that are unrelated to time, but problems that haven't been solved, for example. So Kristen McKiernan and my group did a study a few years ago where we looked at different tasks that varied in difficulty level. And the hypothesis was that the more difficult the task would be, the less of this task-unrelated thinking would be going on. And we describe here a tight correlation between the difficulty of the task, which was measured in different ways, and the frequency of these task-unrelated thoughts that people reported to us just after doing the task, like within a second or two after doing the task. And we correlated that with the level of activation in these regions shown in the bottom figure on the right, which is more or less the default mode network. A tight correlation, meaning that these task-unrelated thoughts are directly related to the neural activity going on in these brain regions. So the problem here, the reason we're not seeing this semantic system when we use a resting control, is that these are regions that are active during resting. So if you take nothing away from this talk other than that, this is my main goal, is to get you to think about not using the resting state if you're interested in these language comprehension networks that have to do with retrieving word meanings and sentence meanings. So tasks are necessary in fMRI language mapping. Tasks guarantee engagement of target processes, so I would strongly encourage the use of tasks rather than passive presentations, as some people are starting to do more and more in children. Tasks are necessary to direct attention to the type of processing that you want the subject to do. And I also strongly encourage the use of overt tasks involving some kind of motor response, either a verbal response or a manual response, because it gives us hard evidence of task performance. And we need that especially in neurologically impaired patients who may not always cooperate or give their best effort on a task. Tasks always engage non-language processes. There is no way around that fact. So we need to incorporate controls for these processes in the task contrast. fMRI language maps vary widely across different contrasts, and this variation is mainly due to differences in the control conditions or baseline that's used in different paradigms. And there are major sensitivity and specificity issues with many, if not all, fMRI activation paradigms. Resting, quote unquote, I always use the quotes, is an active semantic processing state. The subject is actively retrieving images of things, the real world, knowledge about the real world, planning, remembering, thinking. So that's an active semantic state. All right, on to the next topic, which is using fMRI to predict naming ability after left anterior temporal lobe surgery. So this is data from a large study that my colleague at Cleveland Clinic, Robin Bush, and her group did fairly recently. And what you see here are different surgical groups. Each bar is a different surgical group. So the one I want you to notice is the one on the far left, which is the group that underwent left temporal lobe resections of different sizes, mostly standard left ATL surgeries. They're the only ones that show a substantial decline in naming performance. That doesn't even happen with frontal lobe surgeries, not much. And so that's the clinical problem that we're trying to address with fMRI. And the reason that we are trying to address it with fMRI is that other predictors aren't that good. So later age at onset is predictive of a worse decline. Older age at surgery is predictive of a worse decline. So the older you are when you have surgery, the more you're likely to decline on this naming task, which is usually the Boston naming test. It's a 60-item test where you see pictures and you just say the name of the picture. This is neuropsychology, nothing to do with fMRI. And the higher you do, the better you do before surgery, the higher your pre-op score, the worse you're likely to decline also. But when you combine all of those factors into a multivariate model, it only explains 16% of the variance. The R squared is 16.3. Not very good. There's another 84% or so that of variation in the outcome that's not explained by this model. So the question is, can we use language lateralization, just determining whether the language system is mostly on the left or the right or both, to aid in the prediction of this decline? Obviously, that was the original purpose of the WADA test, and so we can talk about the WADA test later if anyone has questions about that. In brief, we've discovered that our fMRI protocol gives results very similar to the WADA test, and it actually predicts this naming outcome a little bit better than the WADA test, and there are various reasons for that. So the first point I want to make is that language lateralization is a graded phenomenon. If you're interested in language lateralization, don't think of it as left, right, or mixed, or left, right, and bilateral. It's a smooth continuum, more or less, from very strongly left to very strongly right, and you can find patients that are everywhere in between along that gradient. So here's an example, and this is just to show some individual patient maps that we get in our laboratory of using that same semantic decision, tone decision protocol that I showed before. And you can see that most of the activation in this individual is on the left hemisphere, and we quantify that using a lateralization index with the formula given there. There are various ways to calculate the lateralization index, and we're using a large data set right now that we have to try and figure out what is the best way, using outcomes as the gold standard. So this patient had a lateralization index of 0.93 on a scale from -1 to 1, meaning strongly left. Here's somebody with a slightly more mixed pattern and a lateralization of 0.47. Here's somebody with a lateralization of 0.23, and you can see that it's getting more symmetrically distributed. And here's somebody with a pretty strongly right lateralized pattern. So we see everything along that continuum in the study. So what we wanted to do was test whether these language lateralization measures add to the predictive value of this multivariate model for predicting naming outcome. And to do that, I organized a multi-center study we called FATES, which is fMRI and anterior temporal epilepsy surgery. It was a prospective study that finished about 2 years ago. We collected surgery patient data at 9 different centers. They all had the same language mapping and cognitive testing before surgery, and then they came back 6 months after surgery to reassess their language and other memory abilities. So we were interested in whether we can develop new multivariate prediction models for language and verbal memory, which I will mention if I have time to do it, and to define relationships between the extent of activated tissue resected and the language and verbal memory outcomes, and I don't have time to show any of that data today. This is one of the main results, and it's going to be a poster here at this meeting. Stop by on Wednesday, and I'd be happy to chat with you about it. You see here 74 patients who went through left anterior temporal lobe surgery, and on the x-axis is their preoperative fMRI language lateralization index, and on the y-axis is their change in this Boston naming test score. So a negative number means that they declined. And you can see that most patients decline, and that there is a relationship between their preoperative language lateralization and the amount that they decline. So if they have strong leftward lateralization preoperatively, they're more likely to have a sizable decline. That turned out to be the strongest predictor of decline, so with a correlation of 0.5. Age at surgery was correlated, age at epilepsy onset was correlated, their education was marginally correlated, their pre-op BNT score, we didn't find a correlation, surprisingly. When we put all of these factors together that were significant, this multivariate model can now explain 40% of the variance. So compared with 16% of the variance without fMRI, we've increased the prediction accuracy to 40%. Okay, everybody likes case examples, so here's a few quickies. This is a person who had a preoperative laterality of 61. We can multiply these numbers by 100. People sometimes like to see that. Age at surgery was a little older. So this is a strongly left lateralized person, a little bit older than a typical patient, education average. The model predicts a change score of -11, so a decrement in their raw naming score of 11 points, and this person had an actual change of -13. Here's a very different example with a strongly right lateralized pattern, younger age. The predicted change on the BNT was actually an improvement of +3, and this happens because people do show mild practice effects, and the model accounts for that. And the actual change in this person was +5. All right, so that's predicting naming outcome. It turns out that this is probably the most clear clinical application of fMRI that's out there. So far, there have been 5 small studies with 25 or fewer patients showing mixed results. This slide I just showed you, these sets of slides, I think demonstrate that the language lateralization done preoperatively with fMRI really does have valuable clinical predictive power. And that's useful for surgeons and for patients, especially in elective surgeries, which surgeries for epilepsy often are. The other clinical problem with left anterior temporal lobe surgery is decline in verbal memory abilities. So the solid lines here show pre and post scores on 2 different verbal memory tests, verbal learning and verbal recall. On both of these, the patients decline compared to baseline, and the right ATL surgery control group does not decline. All right, so I want to suggest that language lateralization is actually useful for predicting this change in verbal memory. Why is that? Basically, the model is that language lateralization lateralizes along with verbal memory. So when verbal memory is, when language is in the left hemisphere, as in this picture on the left, the verbal memory system will also be lateralized strongly to the left. And that's true even when there's bad damage to the hippocampus. So in the middle slide, you see a patient with a small left hippocampus shown by this smaller red box. They have hippocampal sclerosis from years of having epilepsy. And you would think that that would give them a less risk of declining in verbal memory, but it turns out that that's not the case. Because even in such cases, if the language system stays on the left, that little shrunken hippocampus on the left will be controlling verbal memory. There are cases where language is redistributed, or it was natively premorbidly distributed partly in the right hemisphere, and in that case, the verbal memory system will also be bilaterally distributed, and the risk will be lower. That's the hypothesis. And the data confirm the hypothesis pretty strongly. So this is another scatter plot. You see the fMRI laterality index on the x-axis there. And these patients change in verbal learning score from pre to post-operatively. It's a very strong correlation. So it turns out that you can predict verbal memory outcome just by measuring language lateralization. The preoperative score in this case is very highly predictive, but the fMRI language lateralization adds to the predictive value quite a bit. WADA language lateralization in this sample, we did WADA language studies on all of them, also was predictive, not quite as much as the fMRI. WADA memory lateralization was not nearly as predictive, and we can talk about why that is if we have time. Anyway, when you combine those variables together into a multivariate model, the prediction of change compared to the actual observed change is pretty tight. So we use this clinically. We use the same test clinically to predict language naming outcome, and we write a report using these multivariate equations to predict the actual numerical change score for the patient. So, fMRI language lateralization predicts naming outcome. It more than doubles the variance explained by non-fMRI variables, useful for assessing risk in elective cases. Language lateralization predicts verbal memory outcome. So that's because verbal memory lateralization is linked to language lateralization. There's no need, really, if this is your aim, there's no need to measure activation in the hippocampus. Many fMRI language lateralization methods are available. Use protocols, please, that have been validated in some way. Probably against WADA testing is the best way to do that. And I just want to thank all of the people who have helped me with this research over the years. Many of them, some of them shown in pictures here. Sarah Swanson, Dave Sabsovitz are my main collaborators in the epilepsy realm. And we've had nice funding from the NIH over the years and hope that continues. And I've mentioned the 9 members of the FATES consortium down at the right. Thank you.
Thanks, Jeff. So we do have time for a question or two, and if everybody has not figured out how to do this, you go to your interaction, active, whatever, and scroll down to social Q&A, and we did get a question already. Will all the slides of this course be available? And the answer to that question is yes. In addition, there will be a video of the course, so that will be available to all HBM members, I believe. Does anybody else want to try to answer a question? I'll see if I can figure out how to get to it. Okay, all right.
Could just yell out.
Or you could yell out. We actually have time for Q&A afterwards, after the memory talk. So, hi. I'm sorry?
Hi, everybody. I'm going to monitor the app. So if you ask questions, I answered already some questions that you had. Hopefully, everybody managed to see on the GMP3 the answers. I'm sitting over there, so you can let me know if you have problems with it, and we'll try to sort it out.
Okay.
I managed to do it.
Okay, good. Yeah, no, I've got it now. Okay, thank you, Jeff. We're going to go to memory. Okay. Okay, thanks very much. And we're going to go on to memory as well. So there we go. Okay, and that will be me. I'm going to talk in general about memory organization and the various approaches people have taken to mapping memory in the brain. The applications, surgery for temporal lobe epilepsy, as Jeff has already talked about, will often remove the hippocampus, particularly the anterior hippocampus, but we also do removal of tumors that infiltrate the hippocampus or could invade the fornix fibers. So the goal, again, determining if removal will harm memory. And obviously, as Jeff has pointed out, removing a functioning hippocampus will result in memory decline. Removal of a functioning hippocampus when the other hippocampus is non-functional is essentially removing both, and then you get an HM-like amnesia, which we don't want. And then, of course, if you remove the output from the hippocampus, it's essentially a complete disconnection syndrome, and that's just about as bad as removal. So I want to first begin by pointing out that memory mapping is really hard. The hippocampus is very small, and it has even smaller subregions, and these subregions are functionally heterogeneous. So you might say, well, we can go to smaller voxels, and in fact, that can resolve this problem some, but the cost, as you know, will be of reduced SNR. There's also the problem of signal loss in the base of the temporal lobe, and that can impact our ability to see activation in hippocampus. And it's especially bad in entorhinal cortex, and in general, we found it very hard to map any functional activity in the entorhinal cortex, as well as the output fibers there. And then, of course, there are special problems in designing task and control conditions, not unlike the problems with memory. We'll see if some of these, we'll look at some of these specific issues. So there's a unique problem of task design in memory. Maybe it's not entirely unique, because I think Jeff has pointed out well the importance of having the correct activation control in language tasks as well. but in memory, it's, I think, an even bigger problem. So this is an example. This is actually the very first memory activation study that was published. It was actually published with PET many years ago. Here's the task. Memorize a superspan list of words. So in other words, a list of words that's greater than your working memory capacity. And the control task is read a list of words that's matched very carefully for word frequency, for imageability, but don't memorize it. So this is done as a block design, and there's a simple contrast, task versus control. Everybody pull out your apps and see if you can answer questions, okay? We're gonna do a little bit of active. So to go to the active thing, and I'm gonna ask this poll, see if it works. Memorize words versus read words. How do you like this memory paradigm? And you should have 4 choices there. Like the task, don't like the control, like the whole thing, like the task, not the control, like the control, not the task, or are you freaking kidding me? This is supposed to come up with the answer, but it doesn't look like it did. Have people voted? You don't see the question. Oh, great, okay. All right, so the interactive thing, although we have tested it many times, is clearly not working today. So sorry about that. The answer to that question was, are you freaking kidding me? How can you listen to a list of words and not remember it? Does your hippocampus turn off when you say, okay, I don't need to memorize this, I just won't remember it? Of course not. The hippocampus is critical in binding together new information in time and space. It does it all the time, which together forms an episode or episodic memory. It's not going to stop encoding information if you don't consciously memorize. I'm going to talk more in detail about hippocampal function and in particular hippocampal subregions, but we can broadly conceptualize 2 functional domains: domains of processes, such as learning and retrieval, and domains of content, such as verbal versus visual memory or spatial navigation, spatial memory. But episodic memory processes are what are integral to the hippocampus. The learning process is dynamic. I think many of you are aware of this. The hippocampus is crucial for that period of time during the formation of new associations, but as new memories are well established, the hippocampus becomes less and less critical to learning a new memory. The hippocampus is also important during episodic retrieval, again, early in the learning process, and it's involved in reconstructing episodic memories from partial cues. So we do have both encoding and retrieval processes encoded in the hippocampus, at least during the critical early stages of new memory consolidation. Hippocampus is also important in novelty and in discriminating or separating new from similar information. And the main point I want to make here is that different subregions of the hippocampus contribute uniquely to these processes. So what do I mean by episodic memory in particular? And I'm going to answer that question by referring to a series of studies that were done by Laura Eldridge and Barbara Knowlton, using this remember-know paradigm. So this is a paradigm in which subjects are learning a new series of associations, like here they're learning a dinosaur bread, and you can see that the dinosaur is standing on top of the bread. And they're asked the question, and then they have to retrieve these items later, and they're asked the question, did you see a dinosaur? And if the person says, yes, I did see a dinosaur, then they ask the question, do you truly remember the episode? Can you go back and remember that encoding episode? Do you actually remember seeing the dinosaur, or do you just know it? Do you have a feeling of familiarity that you've seen this before without exactly remembering the exact encoding context? So I think all of you have had these experiences in day-to-day life. You'll see somebody and the person's face is familiar. You have no idea where you knew them from. It's just, there's a feeling of familiarity about it. You're correct, but you correctly know the information, so it's a true declarative memory, but not an episodic one. So people can be trained pretty easily to distinguish between these 2 kinds of memory. So for example, if the dinosaur memory is episodic, you should be able to remember other details about the episode. Oh yes, I remember that dinosaur because it was standing on top of a loaf of bread. So that's an example of a true episodic recollection of the dinosaur versus, yeah, there was a dinosaur there. I don't remember any details, but I know that there was a dinosaur. Why do we care about that? In this experiment, they did that long learning experiment, and then they measured fMRI while subjects were retrieving that information. And I'm going to try to use a pointer here to point this out a little bit. So there's a region of interest around the hippocampus. This is done as an event-related design, and you can see the graph of the hippocampal activity during retrieval in these 4 conditions. So when the item was correctly remembered versus when the item was correctly responded to as a memory item, but only with a feeling of knowing, versus a correct rejection and a miss. And what you can see here by looking at the solid red line, it's only those items in which there is a true episodic memory of the item that engages the hippocampus. For those items which were correctly recalled, that is, the person was correct in saying they actually saw the item, but they didn't remember it episodically, there's no activity in the hippocampus. It's as if they never saw it during retrieval. So that points out the critical importance of the hippocampus in episodic memory and not in any other kind of memory. You need to have that episodic component. This, by the way, I'm just going to mention, is something that we incorporate into our WADA test. And as a result, our WADA results are much more specific and quite different than the standard WADAs where you just say yes or no, I saw an item. Then I also wanted to go into the subregions. So I mentioned that the hippocampus is composed of small subregions, and each of these have unique contributions to different aspects of memory processing. I'm going to show you some data in flat space, so just really quickly, I wanted to show you this figure here. So if you look at the hippocampus in cross-section at high resolution, you can see some of these little subregions, and here they are listed in panel A behind you. So you've got the dentate, the CA regions 2 and 3, which are hard to distinguish, so we're going to put them together. CA1 region, the subiculum, and then those regions outside the hippocampus, parahippocampal, fusiform, etc. And in our work, we have segmented these regions, labeled them, and then put them out into a flat space, as you can see here. And in that flat space, you can look at all those individual subregions and see exactly where memory activation is. And by the way, this is work that was done primarily by my former graduate student, Michael Zana, who's going to speak to you later today. And looking at these subregions, there is a very unique circuitry within the hippocampus. And the circuitry, based on animal work and increasingly confirmed in human work, looks something like this. So there's information that comes all around the brain from parahippocampal, perirhinal, and other kinds of cortical regions, and everything goes into the entorhinal cortex first before entering the hippocampus. Once going into the hippocampus, it takes a series of different routes. It can either go indirectly into the dentate, where there are these recurrent circuits, reverberating circuits in the dentate and CA3, or it can go directly to CA1 into subiculum and back again to entorhinal cortex. I'm not going to go into detail on this. I'm just going to show you the bottom line based on a bunch of different works. And basically, pre-entorhinal cortex, what we see is content-specific activation. So parahippocampal place area, fusiform gyrus, you'll see content-specific activation, faces, words, locations. When we get into the hippocampus proper, this indirect circuit that goes through the dentate and the CA1 appears to be important specifically for novelty and basically new association formation. And this is consistent with general encoding processes. These recurrent collaterals are optimized for encoding novel items and associations. The latter part of the circuit, CA1 through a subiculum, appears to be important during episodic retrieval processes, and CA1 also implicated along with CA3 in pattern separation. So here is the paradigm that you most often see in memory activation studies. This is a scene encoding paradigm. This is one version of it that was first put out by Chantal Stern. This is from Michael Zani's experiment. So you just see a bunch of scenes, and you can make a simple decision. Are these indoor scenes or outdoor scenes? And in some blocks, you see all new pictures, and in other blocks, you see the same thing repeated again and again and again. The point I want to make is, if you look at these individual subregions in the hippocampus, you can see that they have very different patterns of activity. So those areas that are outside the hippocampus proper, in parahippocampal gyrus and in fusiform gyrus, care a lot about novelty. And as you can see, every time it sees something new, there's more activation, and every time it sees something old, there's less. In these other regions, in CA2, 3 dentate, and the subiculum, those are in the center, you can see there's really nothing in the beginning, but over time you start to see this learning effect. You can see the activation building and building. And then for this particular task, this is a novelty task, you don't see anything in CA1 and you don't see anything in entorhinal cortex. So the point there is simply that different subregions have very different roles. Here is a follow-up to the Eldridge and Knowlton study. This is the second study that they did with the same kind of stimuli, but they did it during encoding and retrieval, and they did it as an event-related design that you can see here in high resolution to look at the subregions. So we've got at top the bilateral CA23 and dentate, which we believe is involved primarily in encoding new associations or encoding new novel stimuli. And what you see is increased activity only for correct rejections, that is, brand new things, and everything else there is relatively decreased activity or none. In the CA1 and in the subiculum, you see increased activity during the episodic retrieval exclusively. So what this is telling us is that, first of all, different regions of the hippocampus are selectively involved in encoding versus retrieval activities, and specifically they will separate in terms of novelty and in different parts of the hippocampus. This is a region around the whole hippocampus, but it turns out there's a nice anterior-posterior dissociation as well, with the encoding primarily occurring in the anterior hippocampus and retrieval in the posterior hippocampus. So the moral of that part of the story is that if you're to try to do hippocampal imaging and think of the hippocampus as all a single entity and design a task such as a retrieval task and expect the whole hippocampus to show activity there, you're going to be losing most of your signal because only a portion of the activity is going to be active for retrieval. Other parts are going to be active for encoding. And if you average across the whole thing, you won't see much in the area of activation at all. The second thing I wanted to talk about was the activity changing with learning. That is, the hippocampus is dynamic. You know that it is most important early in the learning process, but when things become well consolidated, it's no longer so critical. So, for example, here's the face name association task, a common memory task. We have faces and names together. And they have interspersed learning blocks, so you see a whole bunch of these. In this case, I think we had 7 face name pairs and 4 repetitions of those pairs, learning and recall being interspersed. So you have time to learn over time. And of course, you don't learn everything at once. You might learn 3 or 4 the first time and then another couple after that and so forth. So there is a time course in these hippocampal subregions, and what you can see here is that at the bottom is the actual learning curve, how much information was correctly recalled during each of these blocks. And you can see that activity during encoding very much correlates with the amount of information that's being encoded at the time. So in the first block, the first time you see all the information, there's a lot of activity, but that activity in CA3 and 2 in dentate decreases as the information is well learned. Encoding is in black and recall is in gray, and you can see that in this anterior CA3 dentate gyrus region, it's very specific for encoding. There's no activity at all during episodic retrieval, even though those blocks are interspersed, right? During retrieval, we see the opposite pattern, where in the subiculum there is, again, more activity in the early trials and it decreases, but it's active for both encoding and retrieval, just more during retrieval. And that's in the posterior part of the subiculum, so a different part of the hippocampus, but both of them show these dynamic changes. When we look outside the hippocampus, here, in this case in the fusiform gyrus, because you're seeing faces, you see what we would think of as a priming effect. The first time you see them, you get a strong activation, and after that, it doesn't matter. It doesn't care between encoding and retrieval, and there isn't really a dynamic change after the first item. So, in a sense, it's not really associated with learning, just simple picture priming. So, the hippocampal subregions are then process-specific, and I'm going to show you that in a little bit more clearly. This is in flat space, but I just wanted to show you the black circles there represent the anterior part of the dentate gyrus in CA3. And the top is learn and the bottom is recall. And you can see that all of the activity during learn is in this anterior region, and there is none in those same regions during retrieval, again, even though those blocks are interspersed. So it's highly specific as to process. Another process you'll hear about is that of pattern separation. So this is the old, where did I park my car situation. So you park your car in the same parking garage every day, and every day you've got to separate where you park today from all other days that you parked your car, and that's very difficult to do. Craig Stark has done a lot of research on this, looking at items such as the ones here that are the same item, but they are they're slightly different. And you have to be able to distinguish between the ducky that you saw above in A and the ducky that you saw below in B. So we're going to, so here are the activation maps. And again, I think what I just wanted to show you is that it's highly specific within the hippocampal subregions what we see. So for example, the encoding region in the anterior left CA3 and DG cares about learning new things, so it responds just as much to lures as it does to the first repetition, whereas other regions, particularly in the CA1, respond more to the first and don't respond to the lure. So there's a great deal of location specificity as to this process of pattern separation. So thus far, what I've tried to impart is that the hippocampus is functionally heterogeneous, and depending on the specific task that you use in your approach to analysis, you can easily lose signal, and this is one of the reasons why it's so hard to image the hippocampus. So incorporating your knowledge of the hippocampal functional anatomy as well as behavioral performance into the designs will increase the likelihood of seeing activation. The other big issue in hippocampal studies and memory studies is baseline, and just like it is in language. So the baseline problem is the same as it is for language, and perhaps even more so. The hippocampus, as you know, is part of the default mode network. Activity increases at rest. Why, you might ask? Why does that happen? Maybe you can use your little apps to come up with a theory. We all have theories about this. But there's good evidence that the hippocampal signal is high at rest, and it may even be higher immediately post-encoding. So when you learn a new piece of information, you should get increased hippocampal activation. But when you turn that stimulus off, then your brain really starts to encode that information. It actually increases. Therefore, very highly engaging active rest conditions at baseline are preferred. And Craig Stark has done a number of studies on this. But provided this works, which I would give it like a 25% chance of working right now, given the technology thus far, we'll do a little demo. So one of the tasks that Craig likes to use is the odd-even task. So you see a stimulus, and then you press, and then you see a bunch of numbers on the screen, and you press your left finger for odd and your right finger for even. So everybody get your fingers ready, left, right, because I'm going to show you some numbers really, really quickly. And every time you see an odd one, just push your left finger, and every time you see an even one, push your right finger. It's going to go really fast, so everybody get ready. I'm going to show you a stimulus, hopefully, and then I'm going to show you the task. So here's the stimulus, and get ready, left, right. Everybody, you have to do this because otherwise it's not going to work. It's engaging anyway. Does everybody do the task, sort of? Okay, let's see if the poll works. Which picture of Jay Leno did you see? The left, center, or right? Does this work? What's that? Okay, let me, do people see it? All right, it's not giving me a poll though. It's supposed to show the answers here. Okay, how many people say it's the one on the left? How many people say it's the one in the center? What's that? Okay. Yeah, do you see it? Okay. Okay, 86% were correct. It was the one on the right. It's supposed to show a nice graph up here on the screen, but this thing is really not working. Okay. All right, let's do the same thing, except we're going to use a different baseline. We're just going to look at a circle, and then as soon as the crosshair comes up, press the button. So same thing. It's going to go just as fast Every time the crosshair comes up, press the left, otherwise lift it up. So down for a crosshair. Okay, is everybody ready? I'm going to show you stimulus. Here's a stimulus. So press every time you see it. Okay, let's see if this works. All right, which picture of Meg Ryan did you see? The one on the left, the one on the center, and the one on the right. Can you unlock that and see if it works? Which Meg Ryan did you see? It's supposed to show this up here. Oh my God, it's showing it. In 11 seconds, you'll have your answer. So has everybody voted? Hopefully. God, you guys aren't even close. It was the right. Wow, that's not supposed to work that way. Okay, and now we are frozen. Okay, there we go. Okay, yes. So that did not work so well, but sorry about that. So the harder you work, the more your mind is completely engaged in your task, then the harder it is to encode that information and then hope during the rest period. This is Craig's study looking at the odd-even task versus a rest task, and novel and familiar versus odd-even. And when you do it versus rest, you can see that there's virtually no activity. Those are the dotted lines. And when you do it versus the odd-even task, you can see a significant activation. That's in the hippocampus on the left. On the right is motor cortex. You see the opposite. So the hippocampus is very unique in how it's responding. The motor cortex, of course, cares when you're actually doing it. It doesn't care anything about rest, so that's why you have this pattern. But the hippocampus really does care what you're doing at rest. And if you're just resting, the hippocampus is just going to start encoding that information like crazy. And so actually, we're now experimenting with studies where we show a memory stimulus, we model that, then we have a rest period, we model the rest period, and then we do a distractor, because it's that rest period right after you encode where you really get the activation. So it's very important to care about your control conditions. So I'm just going to show you a couple of studies from the literature, and I'll just tell you that almost everything has been done at the group level. There's almost nothing done at the single subject level. So the most widely used task is this repeated versus novel scenes experiment that Chantal Stern came up with. Here is just one article that has looked at that in surgical patients by John Detry's group. And their task was very similar. It was scenes like this, but they specifically tried to choose scenes that didn't have clearly nameable objects within them. And the control task was a noise control task. And they had both encoding and retrieval blocks. This is what I want to show you. They did an ROI approach, so the above ROIs were hippocampus, and the below ROIs were sort of hippocampus plus, so these extra hippocampal regions. And I'm going to show you their results, and I've put these lines through them and lined them up so that you could see where the activation was in the brain. So on the left shows the hippocampus region, and on the right shows what their actual activation is. And they show that there's first of all, a correlation between fMRI asymmetry and the WADA memory dominance. And they also show what I would call an okay correlation between fMRI asymmetry and the difference in their task performance pre and post surgery. But what I want to point out here is if you look at the area on the left where the hippocampus is versus the right where the activation is, there is effectively no activation in the hippocampus for this paradigm. All of it is extra hippocampal. And again, if you think of that in terms of episodic memory, you can see why that might be a problem. Would I expect them to correlate? Yes, because if the hippocampus is located in the same hemisphere as if a healthy hippocampus, or I should say a lesion in the hippocampus is located in a certain hemisphere, it's going to be correlated with problems throughout the hemisphere, not just in the hippocampus. But if you want to get specific, you really need to see what's happening in the hippocampus. I'm citing this paper that Jeff already showed you, showing that actually verbal memory is predicted very nicely just by looking at language lateralization. And there's another study that shows the same thing from a Swedish group. They definitely correlate, and they correlate pretty well. And as Jeff said, over 40% of the variance. This is another study showing in 57 epilepsy patients, looking at a word encoding paradigm. They actually did this with event-related design and separated out items that were correctly remembered from items which were not remembered, and they analyzed only the correctly encoded items. And again, the fMRI did correlate with postoperative verbal memory decline. It was a somewhat higher correlation. Their algorithm for prediction was also augmented by the frontal language metrics. There are a number of other activation paradigms, only a few looking for right hemisphere memory effects. This is one that was done in children for right TLA patients using this task. So this is a mentalized walking task to different landmarks in their hometown. So they had people look at their hometowns, come up with a bunch of landmarks, and imagine themselves walking through it. They had only 16 subjects, so really not very strong, and they showed a correlation between laterality of activation and post-op memory change. This is the only study that I'm aware of that actually looked at hippocampal subregions, and this is by Paul Yushkevich's group, and a very, very nicely done study. And again, this is differentiating different regions of the hippocampus, particularly the dentate, which is very important in memory encoding, and the CA1, which is primarily important in retrieval. And they show lateralization that's consistent with the seizure size in the whole hippocampus, as well as in these subfields with the strongest evidence in the head of the hippocampus and the dentate. They also found that controls, as you can see here on the right, don't show that degree of lateralization. So again, at the group level, they seem to be doing well. But of course, we don't do activation studies like this for surgical planning at the group level, right? We care about individuals, and virtually all of the studies that are published look at group averaged data. And if you start looking at individual predictive power, you do very, very poorly in the studies that have been published. So I'm just going to show you one case. We're just developing this. We are not at a place now where we're confident doing memory mapping. But this is just one case where we looked at face name association, scene encoding, I can't even remember the lateralization of this case, but any case, during the associative learning, we see this very, very nice, I don't know if you can see that really beautiful dot of hippocampal activation in this patient over here. By the way, this is in radiological standard. And in scene encoding, we see more activation on the right. And if we look at now a region of interest that includes the hippocampal and the parahippocampal gyrus, you can see this massive, massive activation all outside the hippocampus. The reason why I like to show that is because when you see all that massive activation, it's very easy to be distracted by it and to not see what you really do care about, which is what is happening in the hippocampus. But more importantly, I think, is we can look at learning curves, and this is an example of a learning curve during recall in the left and the right hemispheres, and you can see from this that the left hemisphere is very clearly involved in face name association, as is the right to some extent in this patient. This is the anterior hippocampus. Notice again, it's specific to learning, specific to encoding, not to recall. So looking again at these different processes as well as the time series can tell you something about the actual function of the hippocampus, whether what you're seeing is memory per se as opposed to just familiarity or just the actual stimuli themselves, which are extrahippocampal. And I'll show you one weird case before stopping. This is like your classic worst case scenario of all possible case scenarios. This is a right-handed individual with a right hemisphere lesion who Kwon Wada was found to have unambiguous right hemisphere speech. You can see the lesion. His memory scores on the WADA with a right hemisphere injection was 25%, and with a left hemisphere injection, 100%. So he basically looks like he's right hemisphere dominant for speech and memory, even though he's got a right hemisphere lesion. And here is the fMRI memory for the face-name association task. There are no voxels that are found in the left hippocampus at all. These are all from the right hippocampus, and you can see, again, a very, very nice learning curve with TRA1 being most active. And this is, again, the same pattern for both learning and retrieval. So by looking at the learning curves themselves and looking at the specific processes that we know take place within the hippocampus, we can be pretty confident, we hope, that we are looking at an actual learning effect, the actual function of the hippocampus. So to sum up, there are major gaps in the literature. Interpreting extrahippocampal activation is a big issue. That's what most people do when they're doing memory fMRI. There is a big problem in interpreting correlation as prediction. People say fMRI predicts surgical outcome. It's really a correlation. Many of the studies that I looked at involved double dipping, analyzing the fMRI to find regions correlating with memory change and then testing the correlation. They're mostly small n's, very mixed patient groups. I can talk about that later. There's almost no accounting for performance and learning curves during fMRI, and the memory outcome variables, most importantly, are not standardized. Most people use the same pre-op as post-op measures, but of course their learning effects and some of these memory tests are pretty insensitive. And of course the use of group correlations to draw conclusions. So in general, I would say that to date there's really insufficient done examining separate memory processes, hippocampal subregions, dynamic learning, and most importantly, clinical decision-making at the single subject level. And there's very little data on exceptional cases, that is, how do we do with patients with mixed speech dominance, with right brain speech, with non-MTS, non-medial temporal lesions. Although, as Jeff has already pointed out, at least for verbal memory at the group level, language paradigms correlate very well with verbal memory outcome. So is memory activation for clinical fMRI ready for prime time? I think probably not, but I think that we can get there using different kinds of approaches. So with that, I'm going to stop, right? Is that my last slide? Yes, it is. Okay, great. And thank you for your time. And do people have any questions on the apps? Natalie, can you monitor the questions? Do you hippocampal mapping an individual patient for surgery? How do you generate those maps? So we are starting to do hippocampal mapping in individual patients for surgery. We're not using it in the surgical decision-making. We're just collecting the data right now, and we will soon be doing that for everybody. We've only been doing it on a few cases for whom the WADA is ambiguous, or for whom the lesion is ambiguous, such as the case that I showed you. But I believe that we'll be doing them for everybody in the future. How did I generate those maps? Actually, Dr. Washaw will do a live demo of how we generate maps, so you'll be able to see those in a minute, actually after the break. In the semantic task, this is a Jeff question. So I'll go to the next one, and then maybe Jeff can join me for questions for both of us. How frequently do we still do WADA testing? I think both of us should answer that question. So in our group, we still do, we're one of the last holdouts. We still do WADA testing for almost everybody who's going to have a temporal lobectomy. We've agreed not to do the WADA test on rights who were absolutely straightforward right temporal lobe cases. So that is, everything lines up, the MRI lines up, neuropsych lines up, everything lines up perfectly and they're right. Then we will do what we call a skip, go straight to surgery. However, everybody else we do a WADA on. I mean, I wish I had time to talk about the WADA procedure itself because it's done very differently by different groups, and we are very particular in how we do ours. We do multiple items. We do a episodic versus non-episodic assessment of each item, And instead of doing just a forced choice, yes or no, I remember it, we do multiple choice with 4 answers so that the probability of getting anything correct by chance is very low. And then we weight our answers by the degree of episodic recollection that's involved. So we end up with scores on the WADA that have a much wider range and are much more weighted to episodic memory. And so we think that our WADA test actually works very, very well. Other groups have a lot of trouble with their WADAs and they think it's not very reliable, but my own opinion is that's because of the way they do their WADA. For many groups, they just show items and then they do a forced choice, yes or no, remember, which if you start calculating the probability of getting things correct by chance leaves you so little variance that it's no surprise that it doesn't turn out to be predictive. Okay, so Jeff is here? Okay, great. So we can answer questions now for both Jeff and I, and then there was a question for Jeff. Is the semantic task, in the semantic task, what would be recommended for general language mapping? Is it available somewhere?
That's what we use for general language mapping, yeah. And we can make it available to anyone. We've made it available at probably a dozen centers that have asked us for it. Just email me and I can set you up with all the files you need on a Dropbox site.
Great.
And we do WADAs in about maybe 1 in 20 epilepsy surgery patients. Mostly it's people who can't do fMRI for one reason or another. They're incompatible medically with it or have a lower IQ. We use fMRI language lateralization clinically for those other patients. And as I mentioned, we've shown for both naming outcomes and verbal memory outcomes that the fMRI language lateralization is a little better at predicting outcomes than the WADA.
For strong left lateralization, is post-left ATL worse for the intact compared to the sclerotic left hippocampus? Jeff? Let me repeat that question. For strong left lateralization, so you mean fMRI lateralization, is post-left anterior temporal lobectomy worse for the intact compared to the sclerotic left hippocampus?
Yeah, that's interesting. So how much does hippocampal volumetry add to the prediction, I assume, of verbal memory outcome? Because it doesn't make any difference for naming outcome. We've found that it's somewhat predictive for, does anybody do logical memory from the WIMS, for example? It's a little bit better at predicting story memory outcome, and it doesn't seem to have any much at all predictive value for predicting this kind of rote word list learning memory that's often used in the neuropsychological battery. So we don't do it routinely, but it probably has some value. It's just a lot of work, actually. But the answer is generally to the question is, if you have a sclerotic hippocampus and you're left lateralized, your verbal memory is probably not as much at risk, but it still is, at least for that story memory.
Yeah, so John Detry has done some studies of this as well, and I think that the general conclusion, just very broadly, is that to the extent that the hippocampus that you're going to take out is still functional, that's the best predictor of memory outcome, not the intactness of the other hippocampus, unless, of course, there's nothing there at all. So in other words, if your hippocampus is working a little bit and you take it out, you'll have a memory decline. If your hippocampus is working really well and you take it out, you'll have a big memory decline. Most of our cases who come in, by the time they're ready for surgery, their hippocampus is so sclerotic it's like non-functional, but for many people that's not the case. And in the case that I saw you, the lesion case where you have the little cystic lesion, that's not mesiotemporal sclerosis, it just happens to be a lesion at the hippocampus. But it didn't actually impair hippocampal function, as you could see. So you can see all kinds of things. Again, at the individual level, you have to look at each case because you'll get a different outcome. And for Jeff, what measures do you think are missing in the predictive model for outcomes to explain the missing 60%?
That's a great question. I think it has a lot to do, maybe not completely to do with, but it has a lot to do with variation in the location and extent of the resection. So we're doing voxel-based lesion symptom mapping studies now on these patients using post-operative MRI scans and labeling the lesions that the patients get to try and figure out which of the areas averaged across the group of patients. It's going to vary a little bit from patient to patient, but are there any zones in the temporal lobe when they're resected are more likely to produce naming impairments? And there's a lot of variation in, for example, the posterior extent of the lesion. That probably makes a difference. There's that basal temporal language area down in the fusiform gyrus that's probably really important for naming. And if that gets partially resected or completely resected, that probably explains some of the variance.
Yeah, we've had patients, not recently, but in the past, that got that basal temporal resected who had no nouns after that. But fortunately, that's pretty rare because it's posterior enough, and most anterior temporal lobectomies don't go back that far. Okay, how does visualase affect all of this compared to ATL? We don't do are we doing any visualase? Are we? Do you have an answer to that question for UCLA, Dr. Walshaw? So in other words, does visualase seem to do better in terms of outcomes? Do you have that?
Well, we had quite a few laser treatments in the FATES study that I mentioned. There were there were around 90 cases altogether, and about 15 of them had visualase. And as a group, they don't decline on naming, so that's a good thing to know. And Dan Drain's multi-center study showed the same thing. We confirmed it in the FATES study. So the hippocampus in our hands and in Dan Drain's hands doesn't seem to be important for naming. You can take it out and your naming score won't change, but they have exactly the same or almost the same verbal memory decline.
Yeah. And Patty Walshaw says the same thing. Okay. Okay, so that's the end of our questions, and it's also time for a break. There is coffee outside in about 2 to 3 minutes. So let's see you back here at 10:15. Is that right, 10:15? Yes, thank you very much.